Hello, good morning. My name is Cyrus. I'll be doing some presentation for my practicum, my Data Science Practicum for 2021. Okay, so as you can see from here on the screen, I'm working on classification and localization of chest X-ray images using CNN. This is a topic which is close to my heart because I work in healthcare and I've had first-hand experience on how physicians and radiologists go through challenges trying to interpret this kind of images. So having heard that, I have that background and I've seen how most professionals face challenges on this area. Uh, some of them they have we end up having misinterpretation of the chest x-rays, which can lead to medical misdiagnosis even for most experienced doctors and radiologists. So existing methods of reading and interpreting these images classify them into a list of findings, no specifications on their locations or on the images, leading to the difficulties in correlating to the images or these images to the exact location where we have any or those abnormality identified. So we kind of need a solution like yesterday. We need a solution for localizing or localization of these findings on the chest X-ray images, provide meaningful diagnostic assistance or augmented assistance to these doctors and radiologists. So this study entirely focuses on this. It's focusing on providing a solution to the above challenge, ensuring that we have an algorithm, we have a model which can be able to read these images, classify the images, and localize these images, or draw some uh, drawings like circles or even rectangles to the specific area where we have this kind of abnormality. So I decided to use the CRISP approach, the IPM uh, approach, which was introduced in a number of decades ago, because it kind of augments my research. I've divided my research into six different areas. The first point is, the first part is on problem understanding, understanding the problem. The problem here, as I've said, I'm trying to identify, classify images and localize them to the specific areas where those abnormalities have been identified. My second part is on data understanding. My third part is about data preparation. Then there's modeling, then evaluating the model, and finally deploying the model. But at the center of this all is the data. So how do I get the data which I'm going to work with? How do I get the data which I'm going to use so that I can use it with this model and test this model to make sure it's giving me that accurate result. So that's the most important thing. I'll be looking for my data from this. So I got my data from Cargo platform. That is, it's a data for the competition for 2021, and this competition is about the chest X-ray classification and localization. So I decided to be part of this, as I also try to be part of the solution for this challenge which we have at the moment. So collecting this data was really it was really difficult for me because this data is 191 gigabits. I tried to download this into my computer. My computer almost crashed As much as I tried to zip, I didn't really know how to do it in the beginning. It was I was running on the go. So I found a better way of downloading this data online. I went to my account in Cargo and downloaded all the data there. So I was working on this platform. But this still didn't solve my issue because I was still having issues with where I tried to run this my model on this data. It will take a long time to run, and at times I will have difficulties with the internet. So I don't know. It kind of requires stable internet connection. So my main goal was to classify the 14 thoracic lung abnormalities from chest radiographs and localize the critical findings through the object detection and classification. So my dataset consisted of 18,000 scans, of which 15,000 were independently labeled images. For training my model, I used 3,000 of these images to evaluate the accuracy of my model. On the exploratory data analytics point on this area, this is one of the most important part of any data scientist. I was trying to really get a glimpse of this data, understand, at least get to understand what is this data all about. How am I able to read these pictures? I acknowledge I'm not an expert in this area. Uh, I'm I'm running and we'll be running together. So it was really hard. I've never worked on this huge chunk of images. I've never worked on this big uh, load of images before. So when I tried to explore into this, I, I didn't know if indeed I will use the same code which I've used before for this other kind of data. But I tried, and some of them they were working. So, safe, we have online platforms. We have Googled around. Also did cargo around, and I got some of good collaborators who have really done a good job in teaching the world and adding to the body of knowledge of this profession. So this histogram demonstrates various abnormalities as classified. It shows some of the abnormalities identified in these images, and you see we have about 31,000 no findings. So this is the big chunk of the images which don't have, like, there was no finding. Seemingly these are normal images without any abnormality. So we have others with which were identified to have cardiomegaly, others were identified to have aortic enlargement, there is pleural thickening, ILD, mass, pulmonary fibrosis, up to pneumothorax. It seems like pneumothorax was the one with the least number of images identified to have this. So it shows that most of the images have no findings. This is good because when you go to hospital, you don't really want to have this kind of abnormality. So this is what I was envisioning, and I was able to do this. So localization of just images. When you look at this kind of images, these are 500 by 500 image. You see here this rectangle. This rectangle shows a given abnormality here. We also have this rectangle with the gray blue rectangles. This also shows some abnormality. It means like this image has more than one issue. It has more than one abnormality identified. And when you see more than one line of this kind, it seems like the radiologist or different radiologists were able to identify these two abnormalities. So that adds more value. That gives more confidence that if one more than one person was able to identify the same, then it means for sure your model is also able to or has more accuracy. So when you look at this, we also have some minor abnormalities identified here. We also have this one which has seemingly two or three, but it seems like we also have several radiologists or physicians who are able to diagnose or identify this as an abnormality. The same to this. And this one now, it seems like it has more than three abnormalities. So we have purple, blue, and green. The same, this one has purple, that's green, purple, and blue. So this one has more. So the more the number of colors, the more the number of abnormalities. The more the number of similar lines, the more the number of radiologists interpreting this or giving more validation that there is an abnormality identified here. So next is data preparation. So while I was going through my data, I realized like because this was really the first time I was working on DICOM format images, I was really having some kind of difficulty to peep into the images and see exactly what it is. But I realized that I was using the same. We kind of use the same code, the same command, like in other areas. Like here, oh, this is a CSV file of images. The images uh, which which are showing like those kind of abnormalities. So there is kind of classification here: the class name, the class ID name, and the radiologists who have classified this as having no finding or having some abnormality like cardiomegaly. So the first one, when I did this, it gave me nuns, nuns, and this one it means like from the metadata it means like there is these are an empty space. So empty spaces they're not necessarily left empty, probably because there's no data or there's no observation. So I decided to fill this with zeros. I rather fill them with zeros than drop this kind of column, because if I could have dropped the column or the row, it could have done more harm to me and I will lose the validity of my data. So while working on this data, any kind of data as a data scientist, we should be cautious. You should be cautious on dropping any kind of data, because you may introduce an aspect of bias, or you may do more harm to the data and end up coming with your own kind of data, which will not necessarily give you the feedback or the right research which you need. So in this case, I decided to clean my data by adding or replacing the nonce with zeros. I also tried to format my images from DICOM to JPEG, also to PNG, but I realized that while doing my research, I realized that DICOM is the most accepted digital image communication, you know, protocol for any medical. It's called digital imaging medical, like on medical imaging. So I may not really give the right definition of the word, but that's exactly what it means. So I realized like formatting them, changing them to PNG, it's not that hard. It was easy. I changed some of them, but I realized I should leave them in DICOM format, because DICOM format have metadata, have other information in those kind of images, which is really important for you when interpreting these kind of images. So from this aspect of data preparation, I go to modeling. So I built my model on CNN. This is convolution neural networks. Convolution neural networks has three layers. There is the input layer, there is the hidden layer, and there is the output layer. So I built this on, I ensured like I used the protocol, I used some of the code which suggested by some of the corporators or some of the, you know, the good people online. I did build my model and I changed a few parameters to try to see how this model was working. I did this while I was testing though. So I did build the hidden layers which contain configuration with real layer and the pooling layer. The output layer, the rule is performed with nonlinear activation function that says negative input values to 0. After completion, the pooling layer executes the sampling operation. So that's how this is the working mechanism of my model. Okay, I did evaluate this model using uh, by changing the parameters. So this is kind of uh, building the evaluation pipeline was just similar to the training pipeline, only that I changed a few things like catching photos between the epoch. I iterated and created a model by changing the parameters using sigmoid activation. I also tried sigmoid and Reru, and Adam, and I realized like there was kind of some accuracy reduction when I was reducing the layers. This is not necessarily like it happens in the models. It depends on the data and the model. So I did see some little change when I was using Sigmoid and Adam. Also, when I changed the activation, the Reru. So for deployment of this model, I realized this model really works well in a cloud-based platform. It works well because these are pooled uh, distributed memory, which is scalable wherever there is need. If, for example, like my computer is struggling to really work on these images, cloud platforms are scalable enough that they increase the CPU, the the memory, the RAM for those cloud platforms. It changes depending on the need. So you will not have difficulties like the difficulties which I was running into. So this model can be deployed in mostly like in the parks, like in hospitals we have the park system, we have the park server. We can have this deployed there in those platforms and have these images directed to the parks. And during this time, where they are live through kinesis, they can be interpreted and all the results sent back to the physicians or the radiologist for further diagnosis. So the model requires a lot of memory, as I've said. It works best when deployed in the cloud. For the future, I feel like the images may be made possible by archiving because we have several images. We can have all these images archived in the cloud at a cheaper price. so that wherever they are needed, they can be accessed and they can be interpreted. So for summary and recommendations, I think this model is a good one. Initially, I was able to get a prediction of 74%. It kept varying depending when I was changing, but I also reduced the number of the images up to 10. So this was really because I was running into difficulties. So the more the images, the more the accuracy, the more the better the better the prediction. And another thing, when you increase the number of layers, there is more accuracy. There is more. The model becomes more accurate, but it reaches a moment like there is the highest point which it cannot go beyond. So once you establish that, oh, this we get this through trial and error until you arrive at a point where you get like more accuracy. And your accuracy may differ from one model to another, or may differ from one platform to another, or the number of images which are used. So the prediction or classification is faster compared to human classification when using this model. So that's why I'm really suggesting that we adopt this. I don't want us to adopt it blindly though. I want us to do more research on this, because this research and many other research which have been done by you know other professionals who are seasoned in this area have shown a lot of evidence that these platforms, these kind of models, these algorithms gonna do more good to radiologists and even these professionals. So we need to do more research, do more tests, rigorous tests, to prove that indeed there is consistency in the results obtained when we use these kind of models. I also even saw some kind of some guys working on artificial intelligence ways of building this. So this is really good news for these clinicians and radiologists. Going forward, it seems like they're gonna have work cut for them. It's gonna be easy for them. Of course, I don't know. There is an argument, and there is no agreement whether these kind of models they're going to make these professionals go out of work. So that's a discussion for another day. So without much ado, I'm coming to the conclusion of this, and this is my observation. TensorFlow, deep learning, which I used in this case, I use Keras TensorFlow, has helped accomplish significant goals in training our dataset. So we were able to build several utility layers and nodes within each layer. The number of activation layers and the type of activation node were identified to influence the performance of the model significantly. So one way to enhance the performance of the model is to experiment with the different numbers of these elements and parameters. And I guess from my experience, the more the data, the better the outcome. So we can also use machine learning algorithms, employ optimization techniques like hyperparameters, tuning, feature selections, and enhanced feature transformations, which can equally be used for the CNN with TensorFlow and even H2O and other improved deep learning and artificial intelligence tools. So from this model, radar activation was found to be performing better than its counterpart sigmoid. Oh no, not really. It was performing better than it was found to be performing better compared to the sigmoid activation. So, but this does not mean that it's better than anything or better than sigmoid going forward. There is variations on different calculation nodes depending on the model under study. So finally, we have some suggestions for future lessons, future directions. We need to do more research. We need more collaboration with clinicians. We need more research, more collaboration with radiologists. These are professionals in this area. We cannot be better than them. As much as we can, we think of helping solve this kind of challenges, they know more about human health than we do, and we need to cooperate with them to make this a success. We need to have rigorous testing of the model to ensure consistency and success of this model. The model may be improved to become an AI model and deployed in cloud platforms, as I said before. And during this deployment, we should continue to do continuous evaluation and monitoring to ensure that its performance is either improved or is consistent. We should also be careful about the data, patient data, and privacy protocols like HIPAA are really important. So for us to really be successful in this, we need to ensure that we take care of all the regulations which are taken, that were taken care of. So the last part of this is my references. I was really impressed by my seniors, some of the seasoned professionals in this area. I was able to learn from Kaggle, was able to learn from GitHub, I was able to learn from YouTube. There is people of goodwill. There is people who are more than willing to support this profession. They have done much contributions than I can do. But this has given me a motivation going forward, also to change the world, to add my voice into this. They have done a good job, and I will join them as I grow in this profession. Thank you so much. So I think I may go a little and show you some of the work which I did in here. It takes a little more though, so but it's really an awesome. So this is the cargo. This is my account. So these are the data. I was able to download this data. You see the test data is here. It's huge. It's about 3,000 images. So we have 2,970 more. So we have this study, and we have the training. What about the training data? The training data has thousands. How many? 14,970 more. So this is the data I was working with. I did work with this training data and the test data. So let's see if this one can do a few things here and there. See, this is the data I was able to load. The data is 15,000 images, DICOM files, and 3,000 DICOM files here. Then I was able to make a list of this. This is a list. It's called train directory file. So I created a list here. I print the total number of train DICOM files. So I have this list of DICOM files. If you want to know, go here. I question this. I want to know which kind of file is this. I put two question marks behind, or even one is enough, and it will tell me. You see, it gave me this a list. It's a list of DICOM files. DICOM files. You see, this is one. It starts from here. Just takes abnormality reduction. DICOM file. .DICOM. dot all this. Okay, so I'm gonna close this one. Then there's the 15,000 images, the 3,000 images. So I create a for loop here so that I can be able to loop through the files and see what I have. You see, I have all these training. This is the train directory files. So the train file DICOM files are here. So I was able to loop through this. So proceed down. Ooh, this is huge. Okay. So I did generate a training file df with the image directory and this x column, y columns, and I did shovel. So this is how I was creating the images. If I did okay. So I did get some tests generated, and I did create some of the sample. I did create some methods here and functions which were helping me get to move ahead with my data. I also downloaded these CSV files, the CSV files from this point. In fact, those are the one I was working with, this training CSV and the test image. This is the training CSV file, and it has this the information it has the image ID, class name, class ID. So it's able to classify all the image ID, and it's able to classify whether it has an abnormality or it doesn't. So let me look through very fast through my so this is the test files. Also there are the test files, you see. I also looked through those, and I was able to get some images here. So I did get this one from this link, thanks to the guys in Geeks for Geeks. So from Matplot I got this more than DS. I created this image, this kind of file, DS by DICOM read the file, specifically file number 13,999 is this one. So this is the image which is here. This image, by the way, when you go for, like, as we progress, you realize it has huge chunks of information. So unlike data, this is really a huge chunk of information. I'm writing a function to display the image size statistics. So these are the function which I wrote to display all the information about this image, and you see the output it's gonna give me. Okay, so I'm going to get through this, plot this image, and also give me the information about this. In fact, it's giving me it's bringing the data about this image. So these are all these, like, one image has all this information. So it has, I don't really know much about this. I'm in the process of running this, but I know probably going forward as I work more on this, I'll be able to explain and tell you what we have for which all this represents. So these are the images from the .csv file. So I did this way. I did clean my data. I removed all the nuns from here, and it became, I replaced with them 00. So I'm doing some little exploratory, trying to get some of the features in this. I did get the box plot for the radiologists who are working, and it seems like these three are really doing a good job in interpreting the images. That's number 8, R8, 9, and 10. Okay, these are the shape. This is like the dimensions for my file. For the training file, it has 67,914 rows and 7 columns. It's huge. Okay, then now I see this is where I did get the histogram for classifying my images. You see, it has like about more than that 1,000. In fact, going down, going ahead, I'm gonna show how much. No finding that 1,818. So the rest are this new more. Thorax has the minimum of 226. So in fact, I've given you the little glimpse of what I've worked on. So I'm gonna deliver this and submit my file. Thank you.